Hi, this is Aaron Jerome Electronics, a YouTube channel. You are listening to a group called Cusco. They're really from South America. They really do play flutes, and all of their music really is very good. Just buy all their albums. I can't play much more because we got to get into the topic at hand, so bye, Cusco. All right, so what are we doing here? Well, this is, again, the door, the key, the seat belt. But what we're going to do this time is build the prototype. There are two ways we can build the prototype. We can use the simulation as our guide, but I don't think that is as valuable a skill as being able to build the simulation or build the prototype from the equation. And since we have both a unsimplified and a simplified equation, I'm going to simulate building the prototype both ways so you can actually see the difference between what does a simplified version look like compared to an unsimplified version. We're going to be using the breadboard companion. We built those earlier in the course. Each student built their own. They get to keep them, take them home forever. They're about $20 each. And the school is kind enough to purchase them. And this is a kind of a rendering of a breadboard companion. On the side of the breadboard companion, if I can get it to go, is this. Well, we've actually soldered pins here that point down through the board, and you can plug those pins into a smaller breadboard, which is what my students all have. Remember, this represents the switches, so that the switches represent the sensors, so we can flip those switches and put voltage through any of these to simulate an input sensor. And then the output, all outputs, all actuators are represented by lights, and we'll just choose one of these lights and hook that up. Above, we've got 0 volts and 5 volts. Now, the first thing we're going to put together is the unsimplified version. This is the printout that I have students. I actually, instead of using wires, I have my students sketch where the wires go, and then I have them build later. So this is going to be the unsimplified sketch. And this is going to be where we put the actual simplified sketch, so you can see how kind of you use the breadboard companion to power things and to represent the input sensor switches and the output actuator lights. And you can see that I've got some chips on the breadboard there. They are, of course, the 04 inverters, the 08, the multiplier AND gates, and the 32, the adding gates. And so let's talk more about the edge of the breadboard companion and talk about what each of those means. Every chip needs power. Not power for data, but like a toaster and a vacuum cleaner, you have to plug them in. So to power the chips, we're going to draw power from this pin, which is the 5 volts. VIN is high voltage. We don't ever use that because that is the destroyer of 5 volt chips, because generally we'll plug in somewhere between 9 and 21 volts. And the voltage regulator reduces that down to 5 volts so that we don't destroy things. So we will never use the voltage in. The clock is 5 volts, but it blinks, and we don't need it for this particular project. And of course, you've got to ground each of the chips, power and ground them, and we will use the 0 volts for that. Down below, we're going to be using one LED to show what the output is. Switch 4, we're going to assign that to be the door sensor. So it'll either tell us whether the door is ajar, slightly open, open, closed. Below that, we're going to use S3 as the key sensor this time. And S2 will be the seat belt sensor. And S1 could be another sensor, but we have not used it. And so we're not going to use it here. So to summarize, basically 5 volts is the power, 0 volts is the ground. The LED output if things work, we'll be able to see LED light 1 come on. And then S4 is the D for the door, and the K is S3 key. Seatbelt is S2. Okay, so using this handout, which I've given all of my students, we're going to set this up using the unsimplified equation. S4 is switch 4. If we want a 1 for the door, we'll flip that switch up, and that will put voltage through the D line. And I want to label these. These are kind of generic. Well, the D is the D line, the K is the K line, the S is the S line. Flipping switches gives voltage to each of those as needed, simulating the input sensors. Now, I want to point out that these represent the chips. There are 6 gates in this one, meaning that it must be then a NOT gate, which is an inverter, which is an O4. Since we're going to have to nest our AND gates together, as explained in the previous presentation, we're going to need 3 terms, 2 gates per term. That's a total of 6 gates. So we're going to need 2 AND chips because each AND chip holds 4 AND gates. So there's one of them, there's the other one. And of course, we're going to resolve everything at the end, bringing it all down to a single output, adding together all of our ANDs and the results of all of our ANDs, and that's an OR 32. I want to put the unsimplified equation up here at the top, and then we can start building this thing. We need to make NOT D. We've got D, that's S4. We've got D, but we have to flip D to make it a NOT D. To do that, we're going to have to run a wire from D over to one of the NOT gates. So we got D going in, it's knotted, it's inverted. Coming out is going to be NOT D, and we want to multiply that with a K. So here we are coming out, there is NOT D there. And now we want to multiply that with K. So here's K. So I'm going to take a copy of K and hook it up to the other input of the AND gate, and then I will have multiplied NOT D and K. So there it is. NOT D and K are multiplied. But that's only 2 inputs. We need to nest that gate with another gate by connecting the output of the first gate with the input of the other gate, giving us another free input. Before I do that, I need the NOT. Oh, I guess I did it right there. But I also need to NOT S. So to get S to be knotted, I'm going to run it through a different inverter. I've seen students try to run it through the same inverter, but I'm going to run it through a different inverter. So there's S going into an inverter. Coming out of here will be a NOT S, which a little bit hard to see, but I run it down to input 5 on the nested pair of AND gates. And from there, I've got the output of the result. So the result is going to be NOT DKS coming out of 6. I'm going to run that down to an OR gate so I can OR it with these other 2 terms. There it is. I've now hooked it up to the OR gate, and I've got my first triple hooked up to the OR gate. Now I can work on the next term. Next thing I want to do is take a copy of NOT D. I don't need to run D through a NOT gate again because this purple line here is a copy of NOT D. Since it's NOT D, I can just use it again. I can plug into the closest location. And remember, I have got this pin plugged into one of 5 holes, so I could plug into any one of the other 4 holes, or actually 3 now, because this wire is plugged into one of them. So I plugged into a hole over here. This horizontal line actually runs under the board, if you remember how breadboards work. It's running under the board. They're both connected to NOT D. I'm taking a copy of NOT D down and plugging it into this second, or this next chip, the first AND gate of this next chip. I also need to take a copy of K. It's not knotted. The previous copy of K was not knotted. So really all I need is a close source of K, and I can actually plug into a hole into the K row here and bring that down as the second input to the AND gate. Now again, we got a triple, we've hooked up to a double, we're going to have to nest to be able to get a third input for the S. So the nest is just taking the output of the first AND gate, plugging it into an input of the second input. Now we have another way to plug into that. And of course, I need a copy of S. I don't want a copy of not S this time. I want a copy of S. So I'm going to go find the closest source of S, which is just right there, plugging it in. It's not knotted, it's ised. Okay, so now I have this triple term here. I'm also going to hook that into the input of the OR gate that I used before. There's my wire. So now I have this term connected to the OR gate, this term connected to the OR gate, and I actually have another term, and there's no space to plug into another OR gate. So I have to nest the OR gates. So I'm just taking the output of one OR and plugging it into the input, and now I have a place to plug into the OR gate as well. Next thing I'm going to do is build this last term. I'm going to hook into this AND chip here. I need a copy of D. Closest copy of D, I guess I could go through here and get a copy of it, or I can go around the top. I think I decided to go around the top, plugging into one of the other holes, coming around. Now I've got a copy of D. Need a copy of K next. My closest, I'm going to plug that into the AND gate here too. My closest source of K is going to be this orange wire. I'm just plugging into the orange wire. Now I've got D multiplied to K. I've still got to hook up not S, but there's no other places to hook up, so I'm going to have to nest this gate, this AND gate with this AND gate with a little shorty wire. And now I can plug in the not S here. Where is my closest output of not S? That would be this yellow wire here. Just going to hook into that. Now I can hook up not S there. And now I've got an output, which is pin 8 on this AND gate, which I'm going to plug into this nested OR gate, pin 5. And now I've created the entire expression. To make it an equation, I need to make it equal to something. I'm going to take pin 6 and bring it up to the light. I think before I do that, there's one more thing I have to do. I'm not going to hook up that light yet. What I am going to do is power and ground each of the chips. So I need to take a wire for power. I'm going to bring that wire clear over to the other side of the board, and I'm going to plug it in to the, well, there's a rail here that connects underneath the board from top to bottom, but the power connection is always pin 14 on these, so I need to add a power connection to all of those. Next, I'm going to ground the entire thing. So I'm going to ground that one, and ground that one. Several ways you could do it. I've decided to do it through the grounding rail. And now I can hook up my last line, which is going to be the, oh, I forgot to ground that one. I'm going to take the output of OR gate B, pin 6, and bring that up to a light. Okay. Now, this, if your breadboard companion is hooked up to power, you should be able to flip the switches and it should do exactly what the truth table says. On the output of the truth table, whenever there's a 0, the light L1 should not come on. But when we switch the switches to represent rows 2, 3, and 6, the light should come on. The problem is this is an unsimplified prototype, which is a nightmare to troubleshoot. So I don't want to make my students build this one. I think I'll have students build the simplified version instead, which we're going to do next. But I need you to pay attention to all these wires and visualize how frightening it is. I have had students in the past actually build the unsimplified version, but it just makes sense to build a simplified because that saves a lot of different things. It saves time, it saves money because there are fewer parts, it saves troubleshooting, it saves on weight, it saves on cost. There's just a lot of reasons to simplify. So you don't want to build this unsimplified version. Let's go to the other handout. We'll use this handout. We'll use this handout to build the simplified equation. I'm showing you the full breadboard companion on this one, but I'm not going to show you the full breadboard, even though I'm going to hook it together as if the holes were there. The reason is it's just harder to see the wires with the breadboard there, and I will put the breadboard back in a minute so you can actually see how to build the simplified version of this. You may want to pause the video and try to sketch ahead of me as we put this together, because by now you're probably getting an inkling of how to put this thing together. So here it is. I've removed the breadboard, but I'm going to hook it together as if I am plugging wires into the holes of the breadboard. All right, so this is the equation we're going to build, the simplified version. I'm going to teach you how to simplify later. It's very important that you know how to do it. So here's the simplified version, and I'm going to call S3 the D sensor, S2 the K sensor, S1 the S sensor. So by flipping those switches up, I'm turning them on. Up is always on. That's just the standard, the protocol, the tradition, whatever you want to call it. Up is on. Up is also 5 volts, as you can see in the with the little arrow off to the side there. You also need to remember that the truth table has the D on the left, the K in the middle, and the S on the right. It doesn't matter if you wanted to use switch 4, 3, and 2, but you should always use D, K, and S, the variables, in the same order as they were on the truth table, because you have to test the truth table to make sure that it works. Okay, so that means if S3 is D, that means S3 is D. S, the place where you connect the wires. S2 is K, and S1 is S for the seat belts. That's the door, the key, and the seat belts. Okay. Now we're going to make a knotted version of D. Look at the chips for a minute. I've got 6 little gates here. That means this must be an 04. I'm not going to label it, just indicating that this is an 04. We're going to use NOT gates. Looks like we'll need one for the D and one for the S, again, as usual. Down below, I put little X's in 2 of these gates, indicating they're multipliers. Therefore, this is an AND gate, 08 AND gate. We don't need to use as many because we simplified. Down here is the OR gate. I put a plus here to indicate that this is going to be an OR gate, and now we can start hooking this up. I need to knot a version of D. So the dashed line means I plugged into a hole far away from the NOT gate, but since I did and the NOT gate's plugged into the same hole, the wire runs underneath the board to the NOT gate. So there's D going into the NOT gate. Here comes NOT D out, and I'm plugging it into an AND chip, just as indicated on the simplified equation. I also need to hook that particular AND gate up to K, to AND NOT D and K together. So I'm plugging it into the first version, the first source of K, and now I've got D, NOT D, ANDed with K. I am going to skip the OR gate for now. I'm going to take a copy of K, though, and plug it into the other AND gate, because that's what we need. I'm going to the closest source of K. I also need to do something with that S to make it a NOT S. I'm going to use a different NOT gate, plugging in getting out of it a not S, plugging it into the AND gate, and now all I have to do is OR them together. So I'm going to take the output of both of those AND gates, plug them into an OR gate. That's what I've done. Now I also need to connect the output of the OR gate into an LED. So to make the whole thing equal to something, going underneath the board, using a wire to go vertically, connecting to the LED. We don't want to forget the power and the ground, so we've got to hook up to power. I'm using the power rail on the right side and hooking up the power to all three of the power inputs on the three gates. Going to do the same thing with the ground on the other side, hooking up to the ground on each one of those chips. And now I have got the entire simplified version hooked up. Pay attention. It is much simpler to troubleshoot and read and hook this up. Takes less time. It's just a good idea to know how to simplify, and we're going to be talking about two ways to do it: Boolean simplification and K-map simplification. I've already talked a little bit to my classes about each, but we'll get in more deeper into each of those, more depth, a little later on. Putting the breadboard back so you can see I've actually connected to several holes on the breadboard, and that's it. Now, once my students have completed this actually makes a pretty convenient map for actually building the real physical prototype. That's why I have students turn this in so that they can't look at this as they're building the real physical prototype, because I want students not to do monkey see, monkey do. I want students to build from the equation. That's why you turn this in. Okay, so turn it in, and then we'll start building this on the real prototype using the real breadboard companion that you constructed and the real breadboard. That's all I got to say for now. This is Aaron Jerome from Jerome Electronics. See you next time.